Hi, good morning to everyone. In previous session, we discussed regarding stresses in thin cylindrical shells. Okay, in this class, we are going to discuss about thin spherical shells. Okay, what are the different stresses in thin spherical shells and problems regarding this topic. Okay, coming to spherical shells. Okay, in spherical shells, the difference between cylindrical and spherical shells is nothing but in cylindrical shells having some length, but in case of spherical shells there is no length. It is in the shape of spherical shape, that means ball. Okay, observed in this diagram, consider a thin spherical shell subjected to an internal pressure as shown figure. Okay, it is the thin spherical shape. We taken cut section of this part. It is subjected to some internal fluid pressure. Due to this fluid pressure, what happened? The spherical shell may be split into two halves. That is either in x-axis or y-axis. Okay, let us consider where P is equals to intensity of internal pressure and D is equals to diameter of the shell and T is equals to thickness of the shell. Okay, the shell is likely to be torn away along the center of the sphere. Observe here, the sphere may be split into at the center due to here it is the most maximum diameter of the spherical shells. At this region, maybe the spherical shell may be split into two parts. Okay, observe the shell is therefore total pressure acting along the center of the shear is nothing but pressure is equals to intensity of internal pressure into area. It is the force developed in the spherical shells due to the internal fluid pressure, so that the internal fluid pressure is nothing but small p into area of the cylindrical shell, internal area, that is pi by 4 d square, where d is the internal diameter. Okay, next observe, it is the spherical shell. It is a cross section, internal cross section. In one axis we taken as sigma 1 and another axis we taken as sigma 2. Sigma 1 is nothing but circumferential and sigma 2 is nothing but circumferential stress in y-axis. Okay, due to the internal fluid pressure, it will offer the force throughout along the internal circumference of the spherical shape. Due to this, what happened? It will offer some resistance to that internally applied force is nothing but sigma. Okay, we are applying internal fluid pressure along through the internal circumference. Okay, due to this internal force, what happened? It will offer some resistance along its thickness. Okay, we mentioned in arrow marks. Okay, it is the internal resisting forces due to the applied pressure, due to the force due to pressure. That means here the force will be developed due to the internal fluid. Okay, now we are going to calculate the stresses in the shell materials. Nothing but here resisting pressure is equals to total pressure. Okay, what amount of pressure we are applying, the same amount of resistance will be developed, so that by using that stress is equals to total pressure by resisting pressure. Here total pressure is nothing but already we calculated in this equation, that is intensity of internal pressure into area, that is P into pi by 4 d square. Similarly here also substitute that formula P into pi by 4 d square by resisting pressure pi d into T. Pi d means here the resistance offered along the thickness, so that we taken area as pi d into thickness. Okay, next by simplifying this equation we will get Pd by 4T. Okay, whenever we consider the efficiency, so that if efficiency, eta is the efficiency of the riveted joint of the spherical shells, then the stress in this equation you need to add this efficiency, that is eta. So that by considering the efficiency in the thin spherical shells, finally the stress in the thin spherical shells that equals to Pd by 4T efficiency. Okay, By using this formula, we can calculate the stress developed in the spherical shells due to the internal fluid pressure. Okay. Next, coming to changes in diameter and volume of a thin spherical shells. It is nothing but strains developed in the thin spherical shells, that is diametrical strain and volumetric strain. By using these formulas, we can calculate the change in diameter and change in volume. So that where sigma c is equals to PD by 40 and sigma L is equals to PD by 40. Here both stresses will be same because the area along its x-axis and y-axis both are same. So that here the circumferential and longitudinal stress both are same. So that now we are going to calculate the circumference strain. So the circumference strain is equals to longitudinal strain, that equals to E1 is equals to E1. So that now we are going to calculate in x-axis. That means E1 is equals to EC by E minus mu into sigma L by capital E, where sigma C is the circumference stress, capital E is the Young's modulus, mu is the Poisson's ratio, and sigma L is the longitudinal stress, and here E also Young's modulus. In this equation, where sigma C is equals to PD by 40, by substituting in this equation, we take in common, that is PD by 40 into 1 minus mu. Okay, by in this equation we substituted PD by 40, that means in place of sigma C and sigma L, and we taken the term PD by 40, so that we get the final equation for strain developed in spherical shells, that is PD by 40 into 1 minus mu. It means PD by 40 into 1 minus mu is the equation to calculate the strain developed in thin spherical shells either in longitudinal direction or circumferential case. Okay. Next, changes in diameter. Up to now we calculated the strain. Now we are going to calculate the change in diameter. So that ED is nothing but change in diameter by original diameter. So that delta D is equals to ED into D, where up to just now we calculated diametrical strain, that is PD by 40 into 1 minus mu. Substitute this value in this equation, you will get the final formula for change in diameter. So that PD square by 40 into 1 minus mu. Next, coming to volume of a sphere. Now we are going to calculate the volumetric strain and change in volume. For this, first we need to consider the volume of a cylinder, that is 4 by 3 pi r cube. Next, that equals to 4 by 3 pi into we are going to write radius in terms of diameter, so that r is equals to d by 2. In place of r we taken d by 2, so that by simplifying this equation we will get, that is 4 into d cube by 6. Okay, it is the volume of a sphere in terms of diameter. Okay, now we are going to calculate the change in diameter. Change in diameter means by differentiating the volume we will get the change in volume, that is delta V is equals to pi by 6 is common, d cube, that is nothing but n cube, okay, or x cube, that is x power n into x power n minus 1. By using this formula we simplified pi by 6 into 3d square into delta d. This is the change in volume. How it will get means by differentiating the volume we will get the change in volume. Okay, now we are going to calculate the volumetric strain. Delta V is equals to EV is equals to delta V by V. Delta V is nothing but change in volume, capital V is nothing but original volume. So that by simplifying that equation we will get delta 3 into delta D by D, where delta D by D is nothing but diametric strain or circumference strain, that is 3 into ED. By using this method also we can calculate the volumetric strain. It is the another method. In this method also we will get the formula for volumetric strain as 3 into ED. Okay, the first method is enough. Next, by substituting the value of circumference strain in this equation, it means 3 into PD square by 40 into 1 minus mu. In place of ED we place this one. Okay. Finally, we calculated EV delta V is equals to EV into volume, where EV is equals to 3 into PD by 40 into 1 minus mu into pi by 6 d cube. Here PD by 40, it is square is mistake. Okay, here the formula is PD by 40. Okay, the remaining, so therefore by simplifying this equation we'll get the final value of volumetric change in volume, that is P into pi d power 4 by 8 T into 1 minus mu. Okay, it is the formula for to calculate the change in volume in a thin spherical shell. Next, coming to problem. At atmospheric pressure, a thin spherical shell has diameter, the given diameter as 750 mm and thickness as 8 mm. Okay, for this we need to find the stress introduced and change in diameter and volume when the fluid pressure is increased to 2.5 Newton per millimeters. Next, take Young's modulus value as 2 into 10 power 5 Newton per millimeter square and Poisson's ratio as 0.3. Okay, here they given diameter, thickness and pressure. By using these formulas we can easily find out the stress. It means in spherical shell both hoop stress and ordinary stress are same, so that F1 is equals to F2. F1 and F2 is nothing but sigma C and sigma L. The formula for hoop stress, that is PD by 40. Substitute the value of pressure 2.5 into diameter 750 into by 4 into thickness is C. All units are in mm, so that you just substituted. By simplifying this equation we will get the value of hoop stress as 58.59 Newton per millimeter square. Okay, now we need to calculate the change in diameter by using the circumference strain. Delta d by d is equals to PD by 40 into 1 minus mu. Okay, it is the formula for diametrical strain. By using this formula we calculated the change in diameter. That means by substituting all the remaining values, that is diameter, pressure and here also diameter and 4 T and Young's modulus 1 minus mu. Mu is nothing but Poisson's ratio. Okay, by simplifying the above equation we will get the value of change in diameter as 0.22 millimeters. Okay, next, now we need to calculate the change in volume. Okay, for this delta V by V is equals to 3 into PD by 40 into 1 minus mu. It is the volumetric strain for the thin spherical shells. By substituting all these values in this equation we will get the change in volume. Here, except change in volume, we know all the values. It is volume 3 into P is 2.5 into diameter is 750 and to 1 minus mu. Mu is nothing but 0.25. 4 into T is 8 into 2 into 10 power 5 is Young's modulus into volume of a cylinder spherical shell is pi by 6 d cube. Pi by 6 into diameter is 750 cube. By simplifying this equation, the change in volume in a thin spherical shell, that is 145608.33 millimeter cube. It is the change in volume in a thin spherical shell. Okay. Okay. Up to now we discussed the thin spherical shells, the stresses and strains formed in thin spherical shells, and we done one problem regarding the to calculate the stress. Next, change in diameter and change in volume. Okay, in next class we will discuss regarding the thick cylindrical shell. Okay, in previous class we done thin cylindrical shells and spherical shells. Okay, in next class we will solve the thick cylindrical shells. Okay, thanks for watching.